Well, good morning. It is Wednesday, March the 17th. Okay, we're here for just a short time today, and hopefully we're all going to be able to stay safe and just actually have a nice afternoon off. Today we want to kind of just continue to do practice problems, dealing with acids, bases, buffers, titrations, preparing. We still are planning to have the test on Friday. Okay, test on Friday. So, I'm sorry, there's just no time to put it off. So we'll just see. I mean, as I was telling some other people yesterday, I've always been fair with you on grades, so I'm not here to destroy your grades. We're gonna have to have a comprehension survey and figure out what we know and what we don't know. Okay, we just don't have any time to put it off any longer because we don't want to wait until after spring break. And as soon as we come back from spring break, we need to do electrochemistry, and then the review time is more important to me than delving in completely and deeply into the acids and bases and taking more time. So we will have covered everything. It's just how well you have absorbed everything. We just need a little bit more time to absorb, but we don't have that time luxury. So, looking at this, for which acid is the value of the acid dissociation constant Ka the smallest? Anastasia, what did you put for that one? B, acid 2. Okay? Why did you put acid 2? Okay? So when we look at the pH, is the lower pH a stronger acid or a higher pH a stronger acid? Lower the pH, the stronger the acid. And how does that relate to Ka? Dissociate more and have a larger or smaller Ka? Larger. Okay, because if you remember that our strong acids, the Ka is super large, approaching infinity. So the larger the Ka, the stronger the acid, the lower the pH. Okay, so Anastasia, you want to change your answer? One. Okay, because it's got the highest pH at any concentration. It has the highest pH, which means it has the least amount of dissociation, which means its Ka is going to be the smallest. Okay? So maybe make a note, explaining that on beside that particular question, so when you go back and study. Now, hydrochloric acid. Okay? First off, chlorous, hydrochloric, lactic, and propionic. Which one is different than the others? Hydrochloric. Why, Reagan? Because it's the strong acid. All the other three are going to be weak acids. And we know that because we've memorized our 6 strong acids. Okay? Now, what do we know about strong acid, hydrochloric? 100%. So if I have a 1 molar hydrochloric acid, what's the pH of that going to be? 0. Because 10 to the negative 1, or the negative log of 1 is 0. Okay? So which one is that? Acid 2. It's the only one with 100%. Notice 0.1 is 1. 0.01 it's 2. It's the log of 0.01 is 2. The log of 0.1 is 1. The log of 1 is 0. It's the one that's 100% dissociated. Whatever the concentration of the acid, that's the concentration of the H+. That's how we recognize that one. Now, just so I don't have to move the thing, let's do 52, then I'll come back and get 50 and 51. Okay? So 52 says a 25 milliliter sample of 1 molar solution of acid 1 is mixed with 25 milliliters of 0.5 molar NaOH. Which of the following best explains what happens to the pH of the mixture when a few drops of 1 molar HNO3 are added? Okay? Now, a solution, what did we decide about this? Is this a strong acid or a weak acid? Weak acid. So you're going to put a weak acid with a strong base. But Does anybody see what's the difference here between the acid and the base? The concentration's half, right? So if I add in equal amounts of acid and base, but one is half as strong as the other, where are we in our titration? At the half equivalence point, right? You're halfway there, because if it's half as concentrated, it's going to take twice as much, right? So I'm at the half equivalence point, meaning same type of thing here. If I'm adding half, that means I have 50% of this and I have 50% of that. Now this is a base, we're dealing with an acid, but it's still going to be the same type of thing. So what have we formed? Okay, but so we have the acid with the conjugate get base in a 50-50 ratio, so what have we made?
A buffer.
A buffer. So this is one way to make a buffer that's not just mixing the weak acid and the salt of the weak acid. When you're at the 50-50 of a titration of a weak acid, strong base, or a weak base, strong acid, you're going to have a buffer. So, HNO3 is what type of substance? It's an acid. So if I'm going to add an acid, what's going to happen to the pH of my solution? It's going to go down. That's an always. But if it's in a buffer, is it going to go down a bunch or a little? Just a little. So the pH of the mixture increases? No. The pH of the mixture decreases sharply? No. The pH of the mixture stays about the same because the conjugate base of acid 1 reacts with the added H3O+. Okay? That's going to be your answer. Okay? The pH of the mixture stays about the same because the OH minus ions in the solution, well, we don't have OH minus ions really in the solution. It's an acid. Okay? Remember, when you have this is a key point here that I'm about to share, which we've already talked about, but I want to reinforce and stress the importance of understanding this and being able to do this. We'll just say HX is going to H plus X minus. Okay? So if I have a buffer, I'm going to have 50% of this, 50% of this. I'm going to have some of this, some of that. So if I add acid, H plus, what's the reaction going to be? It's going to be X minus plus H plus going back to HX, right? It's going to make it go this way. So this would go up, this would go down if I add more acid. But if I add more base, what's it going to react with? Well, I always kind of say that, but the reality is if you want to write a net ionic equation, you're going to say HX plus OH minus is going to go to HOH, okay, plus X minus. The reality is that this is going to go down and this would go up. I like to think of it as pulling this out and then forcing the equilibrium to the right, but if you have to write a net ionic equation, this is the equation you're going to write for the base. So this is adding acid. H plus, and this is adding base, OH minus. In these multiple choice and free response questions, they like to ask questions about write the equation for the reaction that will occur when an acid is added to a buffer or when a base is added, because they want to see, do you know which part is going to react and why it's shifting left or why it's shifting right. So if it's an acid, now if we have a basic, if we have that CH3NH2 plus H plus going to CH3 NH3 plus. Okay, so that's when I'm adding acid to the base. So now I have my buffer of this and this. Which one is this going to react with? If I add more acid, which one of these is it going to react with? That one, right? If I add more base, okay, if I add base is always going to be which ion? OH minus. Since this is the base, and this is the conjugate acid, which one is the base going to react with? The conjugate acid. So it's going to be CH3NH3 plus OH minus to make what?
Water and CH3NH2.
Yes, perfect. HOH or water. Okay, now again, it doesn't matter which order you put these in. Does that make sense? We need to be able to write these equations. If you have a buffer, it's always going to be an acid and the salt of the acid, or a base and the salt, here it is, the base and the salt of the base. Acid, conjugate base, base, conjugate acid. If you add acid, it reacts with the base. If you add base, it reacts with the acid, whichever part of the buffer. And it's always going to be plus H plus or plus OH minus. Does that make sense? You with me on that one? Woo! Time is fine. We're almost ready to go home. 51. If equal volumes of the four acids at a concentration of 0.5 molar are each titrated with a strong base, which will require the greatest volume of base to reach the equivalence point? Okay, so we have each of the four acids are at 0.5 molar. So we have these four acids at 0.5 molar, and we start adding concentrated base to all four of them. Which one's going to take the most? Acid 2 because it's the strongest one?
Yeah.
Do we all agree on that? Who's saying no? Nathan, what's no?
Wouldn't they all be the same?
Why?
Because they're all the same concentration.
So they all have the same amount of hydrogens. Now they're attached. And this is, we talked about this the other day. It doesn't make sense. You would think the strongest acid is going to require the most, but remember they all have the same concentration, the same number of hydrogens. It's just when you put the strong base in there, it pulls the hydrogen off of the acid where the water's not able to do that. Okay, very good. And I appreciate the fact you're willing to stand out on an island when everybody else was saying the other answer.
What question was that for?
That's 51.
We need to do 50 though.
I'll come back to it. I thought we had already done it, but we had done 49. Okay, so 51. They're all the same. I would bet you $1. You'll see something like this question on the AP test. This is a favorite question. Okay? Because it goes against common sense. And so it's a misconception that the AP tries to correct on that. Okay? Is everybody good? The same thing would be true with weak bases or a strong base with the amount of acid it's going to take. If they're the same concentration, it's going to take the same amount. MAVA equals MBVB works for weak acids and strong acids, weak bases and strong bases. Now, let me just say one last thing as far as writing equations on that. This isn't part of the question, but I just thought about it. If I have HNO3 plus NaOH, that's going to make, obviously, NaNO3 plus H2O, HOH. Okay? Now, if I wanted to write the net ionic equation for this, aqueous aqueous, aqueous, liquid. We know that since this is a strong acid, it's going to ionize 100%, right? So it's going to break apart. This is going to break apart. This is going to break apart. So these are my spectators. So I'm going to have H plus OH minus going to H2O. And it's really, a lot of times you can do it like this because it's going to go so much to the right. Okay? So this is the net ionic. But what if it's HNO2 plus NaOH? What's that going to make? NaNO2 plus H2O. But what type of acid is this one? Weak. Do weak acids ionize to a large amount? No. So we're going to keep weak acids stay together when we're writing the ionic equation. So I'll do a total and a net on this one. The total is going to be HNO2 aqueous staying together because it's a weak acid. This is the ionic strong base, so it's completely broken apart. This is aqueous. This is aqueous, so it's the alkaline metal, so it's broken apart into Na plus NO2 minus. And then water always stays together. So what's my only spectator?
Sodium.
The sodium. So when you have a weak acid, it's going to be HNO2 plus OH minus goes to H2O plus the NO2 minus. Okay? So the whole thing is this, with a weak acid, it stays together. Same thing for a weak base, it stays together. These type of questions are asked all the time. Therefore, you probably should be ready for this on Friday. Okay? Strong acids break apart 100%. This is the net ionic for any strong acid, strong base reaction. It's always H plus, OH minus makes water, and then you get some kind of aqueous salt. That's the spectate neurons. Because the conjugates of strong are weak and they don't do anything. Okay? But when you have weak acid or a weak base, they stay together. All right. 50. Of the following species, which has the greatest concentration in a 1 molar solution of acid 1 at equilibrium? Okay, so acid 1 we said was a weak acid. HX. H plus. Okay, and we're starting with 1 molar of this. But since it's the weakest acid, what does that mean about the amount of ionization? It's little. So which one is greater, HX or X minus? HX. We're not producing a whole lot of H plus either, are we? If we had 1 molar H plus, the pH would be 0. So we have way more HX than we do H plus or X minus. And obviously, if it's an acid, we're not gonna have hardly any OH minus. Now everything would be reversed if we were talking about a base. So what's the answer? C, acid 1. The conjugate base is the X minus. Y'all? Those of you watching online, at home, across the world, this is a very important series of multiple choice questions. That it's really important for you to understand the concepts in this set of multiple choice questions. Are you understanding what I'm saying? Okay? Very important that you know how to do these. Very soon. Is there anything on the back? Oh yeah. Oh yeah, we haven't talked about this, so this is a good introduction on this one. Oh yeah, we have this is in the line, by the way. Okay? Data collecting during the titration, 20 ml sample of a 0.1 molar solution of a monoprotic acid with a solution of NaOH of unknown concentrations are plotted on the graph above. Based on the data, which of the following are the approximate pKa of the acid and the molar concentration of the base? Okay? Now, how do I get pKa? Half equivalence point. So we know the equivalence point's right around 20, right? So the half equivalence point's here. So we hang a left. So what's the pKa going to be approximately? 4.7. You got a 50-50. So, 4.7 is obviously that. So now we look at the concentration, okay? Took 20 milliliters of 0.1 molar of an acid, okay? It took 20 milliliters of the base. So what does that mean its concentration is going to be? 0.1 molar. MAB equals MBBB. Now, what is, gosh, we haven't done that either. Probably gonna leave that out. Look at, what's the pH up here? 13, right? Which means that the pOH is about 1, which means that the OH minus is about 0.1, right? It's about 0.1. Because once we get past the equivalence point, now we're just pumping in a bunch of OH minus. So it's going to be about the pH of our concentration of this strong base. All right, I was going to tell myself, God, I haven't shown you one part. And then we're going to have a practice problem the rest of the video. We've learned how to calculate the concentration or the pH right here. Okay, this is just a weak acid. This is the square root of the initial concentration times Ka. Is how we would get that. At the half equivalence point, we know pH equals pKa. Okay, so we can figure out pH and Ka and all those things from half equivalence point. Yesterday we did the equivalence point. That's probably the most in-depth one because you have to find the K, in this case it would be the Kb of the conjugate by using Kw over Ka. You have to find the diluted concentration by finding how many moles of acid or how many moles of base were added divided by the total volume. Then you plug that all in to our weak acid, weak base, and find the pH. Okay? I want us to do one more practice of that here in just a second. But what about the pH at 30 milliliters? So what's the pH after 30 milliliters has been added? That's the question. So if you want to add this to the bottom of this page, just so you can see that I'm relating to the same graph, same information. Milliliters is added or added? Are. Now we already figured the concentration is 0.1, so we know the concentration of the base is 0.1. Where's the equivalence point? 20 milliliters, right? So how many milliliters excess do we have? 10 milliliters excess. So molarity times volume is equal to moles. So I'm putting in, well, I can just keep it in milliliters here. 10 milliliters, and that's my excess, times my 0.1 molar. This is for the NaOH. excess NaOH. But what volume is it in now?
50.
Because we started with 20 milliliters of the acid, and we added in 30 milliliters of the base, so our total volume now is 50 milliliters. So we have 1/5 of 0.1, which makes it what? 0.02. So that's the concentration now of my NaOH in the solution right here. Moles divided by liters, but it's basically a dilution problem. You use the milliliters of excess. How far past the equivalence point are you? Times the concentration of the whatever you're adding, the acid or the base, divided by the total volume. Now how do I find the pH?
And negative log
Okay, so that's going to give me the
POH.
pOH, negative log 0.020. And what does that equal?
$1.691.
1.7 then, okay? So therefore pH is equal to 12.3. Which is pretty close to what, and these graphs are not 100% accurate as far as on the scale, but it's pretty darn close. Okay? So to find the pH at the fourth point, the past the equivalence point, use milliliters of excess. Not total milliliters. You don't use the 30 milliliters. You use how many milliliters past the equivalence point. So equivalence point was 20. We went to 30, so we had 10 milliliters excess. Times the concentration of the base, which is either given or we calculated it, divided by the total volume. And since it's a strong base, whatever the concentration of the NaOH is, that's the concentration of the OH. Just take the negative log and you get pOH and pH. All right? Now, I will tell you there's a bonus on the test. If you can say, like, what's the pH going to be? Now, I'm not giving a graph, but after 5 milliliters or 10 milliliters, a given amount is added, or so many moles are added. Okay? And so, it's just going to be shifting the equilibrium, HX going to H plus and X minus. HX is going to go down by however much you add. X minus is going to go up by however much you add. And then you just kind of figure that out. But there was an example in the textbook, I think I pointed out to you on that, if you want to learn how to do that. Okay? And let's spend the last 15 minutes seeing how far we can get on this problem. And this has the bonus on it. This was actually a problem on an old test. My test. I've since modified the test. All right, we'll go over this tomorrow. So y'all have a great day and go Jags.